Newton's laws of gravity. Gravity is a field force, which means that it acts at a distance, in much the same way that an electric field or a magnetic field might. Gravity provides the centripetal force, keeping planets, moons, and satellites in their orbits. It always acts from the center of the two objects, which means, like let's say over here, that we had a satellite that was orbiting 10 miles above Earth's surface. If you were measuring the gravitational force, you wouldn't say that they're 10 miles apart. You would have to measure from the center of the satellite to the center of the Earth. So you'd have to also take into account the radius of the Earth when measuring how far apart they are, because you're measuring from the center to the center. Gravity is always attractive and cannot be shielded or canceled, which means that anti-gravity doesn't mean that gravity doesn't exist and cannot cancel out gravity. It can just cancel out how you interpret or feel gravity. Gravity increases with mass, so more massive objects have more gravity. And it decreases with distance, meaning that the farther away you are, the less effect gravity will have on you. Newton's law of gravity describes the force between any two point masses. Here's the equation. In this equation, r is representing the distance between the centers of mass of the two objects. This actually leads to a common misconception when you have two objects, let's say, that are 10 miles apart. A lot of people want to imagine that the radius in between them would be 5 miles, but that's incorrect. If you think about it, we're learning about circular motion, and as one object orbits the other, the distance between them is the radius of its motion, which is why it's listed here as the r is the distance between the centers of mass of the two objects. In the equation, m1 and m2 are referring to the masses of the two objects in question, and this g is representing the universal gravitational constant. You'll see that this constant is 6.67 times 10 to the negative 11th, which is an incredibly small number. And what that does is it scales down our calculations so that gravity is appropriately a very small force. In physics, gravity is considered to be the weakest force, so this gravitational constant helps it to be appropriately weak compared to the other forces. Gravity is an inverse square law, and that's referring to the fact that the denominator has the radius squared. For example, if you were to double the distance between two masses, the force between them would change by a factor of 4. Other examples of the inverse square law include a flashlight becoming weaker as you walk away from the wall, or when you're dousing Barney with a hose. As he gets closer, he'll feel a stronger rush of water, and as he increases his distance, the strength gets weaker. You can see in this graphic that as you move farther from the source of gravity, that its effects are spread out over a larger and larger area. It's a common misconception that the larger planets will have a different force of gravity on other planets. For example, that the force of planet Y on planet X would be less than or more than the force of the magnitude of planet X on Y, when in actuality, these two planets would have the same force. This makes sense, especially if we put in some fake numbers. Let's say that this planet has a mass of 2m, let's just call that 2, and this has a mass of 1m, let's call that 1. And we'll make the difference between them, let's say 3. If we were to calculate the force of gravity on planet X, we would have g times 2 times 1 over the distance between them squared, which would be 2/9 g. If we took a look at planet Y, we would also get g times 1 times 2 over 3 squared, which would give us 2g over 9. These are equivalent forces, and that makes sense because for every action, there's an equal and opposite reaction. So as planet Y applies a force on planet X will experience that same force. What that also means is that the sun applies an equal force on the Earth, that the Earth applies on the sun. If the gravitational force between two asteroids was 1 million newtons, what would the force be if the distance between the asteroids were doubled and they were moved farther apart? Remember that gravity has an inverse square law, so as the denominator becomes doubled, the force would be decreased by a rate of 1/4. So the answer would be A. Here's an example problem. Jupiter is absolutely huge, but is also pretty far away from the Earth. What force would Jupiter's gravity have on you at birth? And how would this compare to the gravity that a nearby Coke machine would apply to you? Let's say that you were standing 10 centimeters away from that Coke machine. I got 5.94 times 10 to the negative 6 newtons. From the Coke machine, I got 2 times 10 to the negative 5 newtons. That means that at birth, that standing next to a Coke machine will provide you with 3 times as much gravitational force as Jupiter might, which to me was pretty surprising. But it makes sense because Jupiter is so much farther away. Another example, Tom has a mass of 70 and Sally has a mass of 50, and they're standing 20 meters apart on the dance floor. Sally looks up and she sees him. She feels an attraction. If the attraction is gravity, find its size. I would fill those values into my gravity equation, and I got 8.75 g, which is approximately 5.83 times 10 to the negative 10th newtons. Just like the force between the Coke machine and the baby and gravity of Jupiter on you, this is an incredibly small number. So this helps encourage the fact that gravity is super small. And even though you standing next to someone would experience some gravity, that gravity is essentially nothing compared to the other forces at play, such as the applied force or friction or force normal, things like that. So the objects around you do apply gravity to you, just at a very, very small rate. A common question I get is, when do you use each of the two equations? This gravity equation here, force of gravity is mass times the acceleration of gravity, or 9.8 meters per second squared, is used when you're measuring the attraction between Earth and something's on Earth's surface. So if here's the Earth's surface, and on its surface there's a elephant, let's pretend this is an elephant, you would use this equation to measure the attraction between the elephant and Earth's surface. This equation right here, g m1 m2 over r squared, has capital G, which is 6.67 times 10 to the negative 11th, or the universal gravitational constant, and is used when you're measuring the attraction between two objects. So if there were, for example, 2 elephants on Earth's surface, you could use this equation to measure their attraction to each other, or even to 2 celestial objects, such as like the Earth and like a satellite. You could use this equation to measure the attraction between these two. Here's our next example. It says a 60-kilogram person stands on each of the following planets. On which planet would her weight be the greatest? Since her mass is not changing and her mass is 60, what this question is essentially asking is which of these planets would have the largest acceleration of gravity. So if you look at these planets, you'll notice that this says M and R, 2M, 2R, and 3M, 3R. That means that of these 3 planets, that A is the densest because its radius is small. And as the object's radius increases, their volume is increasing at a larger rate. This object here is the densest, and that would allow it to have the greatest weight. Let's take a look at why. The value of little g is calculated based on these 2 equations, this and this. Since they both equal force gravity, you can set them equal to each other. And when they're equal to each other, the mass of the object cancels, meaning that you're left with the acceleration of gravity being equal to the gravitational constant times the mass of the planet divided by its radius squared. This is an inverse square law, which, as you remember, means that as the object's radius gets bigger, the force of gravity gets smaller and smaller. So in our previous example with the 3 planets, it reinforces the idea that this planet would have the largest amount of gravity. This leads us to another fun fact. How fast would you have to launch something for it to orbit a planet? And you can actually calculate that by setting the force centripetal equal to the force gravity, giving us mv squared over r equaling g m1 m2 over r squared, and simplifying to this velocity. This velocity is the specific speed a satellite needs to maintain a circular orbit of radius r about a larger mass m. You can also use this technique to find the period of its orbit, or how much time it would take a satellite to travel around. And you can also calculate how fast something would need to be launched to escape orbit and move off towards another celestial object. So instead of a satellite orbiting Earth, sending a space station off towards the moon, for example. The Cavendish experiment was performed by Henry Cavendish and was the first experiment to measure the force of gravity between 2 masses and was used to calculate the universal gravitational constant. He measured the attraction between 2 small balls and 2 larger balls on a torsion balance. What he did was he created like a mobile with, here's the ceiling and here's a string, and here's a wire that's connected to 2 small spheres. Having the spheres on the floor would mean that they would interact with friction, but having them suspended meant that they could rotate freely. Cavendish discovered that when he placed 2 large lead spheres nearby, that the system rotated such that the small spheres moved towards the larger spheres in a method that implied gravitational attraction. And from this gravitational attraction, he could calculate the value of g, since he knew the mass of the 2 spheres and the distance between them. He could also use this to extrapolate and therefore determine the mass of the Earth. These 2 video clips do a really great job of explaining this experiment and the impacts of its results.